Thank you for the introduction. I would like to talk to you about the ultramafic land profiles, specifically Alnöites from Alnö complex and in Sweden and Klunst quarry in Germany. The aim of the study is mineralogical and geochemical reevaluation of Alnöites through comparison of geodynamically similar locations, but locations with age disparity of more than 400 million years, different occurrence of Alnöites, and different associating rocks. You can see that Alnö is a quite nice, evolved and complicated volcanic complex. It's been dated at 584 million years compared to Klunst quarry, where dikes of ultramafic land profiles, northwest, southeast trending dikes, that been dated to 130 million years. In Alnö complex, you can also find carbonatites in the northern parts, but contrary to Klunst, where ultramafic land profiles do not immediately associate with any other rocks, and their age puts them in a bit of a weird spot in terms of Bohemian Massif. Both of these complexes are rift-related. In case of Alnö, it's a breakup of Rodinia supercontinent. For Klunst, it was very early stages of extensional movements that later led to opening of the Eckere Rift in Bohemian Massif. Petrographically, these rocks are indistinguishable from one another, as you would expect from the same rock type. But for Klunst, we have identified macroscopic carbonate nodules present in central parts of dikes of ultramafic land profiles in the quarry. Both localities share a mineralogical similarity in that the melilite is absent, while melilite is still considered a major constituent for Alnöites. We took a leeway to sort of close our eyes on this requirement. Otherwise, our samples fit very nicely for Alnöite. They can be pozonites because we have an abundance of clinopyroxene. We don't have enough carbonate for ilicite, and we don't have nepheline or alkali feldspar for dantianite. There is a difference in evolution stage of these rocks, coming from the absence of amphibole in Klunst samples, while amphibole is quite common in Alnö ultramafic land profiles. Biotite is present as a xenochrist and euhydrophenochrist up to first several centimeters in size, or as microphenochrist making up the majority of matrix. And in Klunst, we have also observed poikilotic phenochrist that enclose other matrix minerals. In terms of classification, most of our points plot in the phlogopite field. We see for Klunst some trends towards tertiary phlogopite. In variation diagram for titanium and aluminium, we fall within the ultramafic land profile field. And we have some samples aligned around 0 for titanium dioxide. Those samples are specific to Klunst samples, and they are these reaction rims on the edge of phlogopite that created when phlogopite reacted with magmatic calcite. Pyroxene is present as diopside and augite, and in variation diagram for titanium and aluminium, we nicely follow the ultramafic land profile trend, and it's present as large, up to first several millimeters in size, phenochrist, making up and microphenochrist making up a matrix alongside of phlogopite. In the bottom picture, you can see highlighted feature that had been described by an older study done on the Klunst samples, and that is carbonate ocelli, which is a cell where magmatic carbonate overlaps and is intergrown with phlogopite, cyanopyroxene, and apatite. and it had been interpreted as evidence for a segregation event of silicate lamprophyric melt from carbonatic melt. As I mentioned earlier, amphibole is completely absent from Klunst samples. Olivine had been present at some point, but today it's only present as pseudomorphs and is completely altered. So all our data for olivine and amphibole come from our Alnö samples. Olivine is dominated by forsterite component, and amphibole belongs to magnesium hastings-ite, pargasite, kersutite series. Stable isotopes of oxygen and carbon from Klunst samples have been measured in carbonate nodules that I have mentioned earlier. In total, 3 carbonate nodules have been separated and 2 carbonate veinlets that we suspected it might be of magmatic origin. And the projection points for this analysis fall within the primary carbonate field. They line up in a similar trend to Alnö carbonatites. And here you need to keep in mind that these points are specifically from calcite. They are not the whole rock data as they are for Alnö, where the stable isotopes have been determined from carbonatites, so from rock. In whole rock geochemistry, we noticed that our Alnö samples form 2 groups. One that we refer to as a group with higher carbonatite affinity is around 25% of silica, and the other one overlaps with our Klunst samples around 35% of silica. On the niobium thorium variation diagram, we are nicely on mantle array. We do see some enrichment trend in thorium, so we investigated if we have some meaningful crustal contamination or crustal input. This gray field, number 4, is specifically Saxo-Thuringian upper crust, but the average upper crust or global subducted sediment would plot in a similar position. So also based on this, we can rule out any meaningful crustal contamination in our samples. Spider diagram for rare elements normalized to chondrite show similar and pretty much identical enrichment trends and patterns for both locations. We can see the red ones are from the older study that I mentioned. I included it here because it nicely fills up otherwise empty space between our Klunst and Alnö samples, and it also showcases the fractionation happening in Klunst samples. Primitive mantle normalized trace elements further reflect the mentioned different carbonatite affinity in our Alnö samples, where we can see elevated values for lanthanum, cerium, but mainly and interestingly for phosphorus, which is reflected, or it reflects the abundance of apatite in Alnö carbonatite, and it is also visible here in ultramafic lamprophires. Whole rock radiogenic isotopes are particularly interested. We can see that we, for both locations, plot pretty much in the exact same spot relative to mantle end members. This was the first clue that we really are dealing with the same rock type produced with similar, from similar mantle source and through similar processes. We have some effects of alteration from mainly in literature data, but otherwise we have very minimal variations in strontium as well as in neodymium. In lead isotopes, we see that we are lying on a line somewhere between depleted mantle and high mu. Our Klunst samples are tilted slightly towards the EM1 component, so we had this indication that we are dealing probably with a 3-component mixing. In 206 LED and 207, we can see a strong overlap for both locations, further confirming that we are dealing with rocks formed from similar sources and through similar processes. 208 is slightly different, and we interpret this to be effect of carbonatites, which are beside apatite rich. They are also the thorium rich and quite radioactive in Alnö. And here in three-component mixing model, we see that our samples form parallel trends. They would probably overlap as roof tiles, so not in perfect overlap, but we have confirmed as the main components depleted mantle and high mu, with the minor input of EM1, as we do not steer towards EM1, but we are brought towards high mu and EM1 mixing line. So to save a little bit of time and to conclude, the most important conclusion is that we, despite the differences, the complexes or the smaller occurrence in Klunst showcases, we still are dealing with the same rock type and produced from the same mantle sources through same processes, and this is evidenced by our radiogenic data. For Alnö, I think we are first to provide lead isotopes. Thank you for your attention.
Thank you, Adam. That was in time, so we have more time for questions.
Hi, nice talk. I was wondering, do you see any evidence for melilite, like pseudomorphs or something like that, or like secondary sodium-bearing minerals?
No sodium-bearing minerals, and I haven't really seen even pseudomorphs, or that's the problem, that I didn't see any evidence of melilite whatsoever.
Yeah, I have a similar problem with similar ultramafic rocks, which are also alnöitic, so that seems to be a common problem around here.
Yes, seems so.
All right, thanks.
Thank you.
Thank you. So if there are no further questions, okay, then one short question.
Yeah, thank you for the talk. Just to follow up on the melilite. So you didn't see melilite in the Alnö samples, right?
No.
But that's just because you didn't take the right samples, I suppose? Because alnöites are supposed to have melilite.
Yes, that's what we wanted to expand on, because I know of work done by Kresten et al. From 1981. I'm sure you are familiar with it, where they mentioned that even most rocks that should be alnöites from Alnö do not contain melilite.
Yeah.
That's why we wanted to look at rocks from two completely different localities. That what do they have in common? What do they have? What are the differences?
Yeah,
and
I think at Alnö there's things like kimberlitic alnöites, ilikites. So there's many different types of ultramafic lumprifiers. So
yes.
you just were unlucky. You didn't get the ones with melilite, I guess. Yeah.
Yes, but then there's the issue. How exactly do we classify these rocks?
Yeah.
Because they don't have enough carbonate.
Well, if you don't have melilite, then it's not an alnöite.
Yeah, but the IUGS classification correctly points us towards ultramafic lumprifiers, but then we don't have melilite, and we can't put them in any of the four categories.
Thank you.
Thank you, Adam. It's your applause.